Right now, there's probably a battery within arm's reach. Your phone, your laptop, maybe a remote control. And you probably think those batteries are storing electricity just sitting there full of it, waiting to pour it out. But here's the thing. Batteries don't actually store electricity, not even a little bit. There are 0 electrons sitting inside your battery waiting for you. So if batteries aren't storing electricity, what are they doing? The answer involves a dead frog, some feuding scientists, and a chemical trick so clever it powers basically everything. It's 1780 and an Italian scientist named Luigi Galvani is poking a dead frog with metal tools. Suddenly, the frog's leg twitches. Galvani is stunned. He calls it animal electricity, convinced that living creatures carry some kind of electric spark, but his rival, Alessandro Volta, thinks Galvani has it completely wrong. Volta suspects the electricity isn't coming from the frog at all. It's coming from the metals touching the frog's wet tissue. 2 metals, 1 moist substance in between. That's the secret. To prove it, Volta stacked alternating discs of zinc and copper, separated by cardboard soaked in salt water. He touched wires to the top and bottom. Electricity flowed. No frog required. This was the Voltaic pile, the world's first true battery. And Volta had just proven something revolutionary. You don't need living tissue to create electricity. You just need 2 different metals and something wet between them. This simple discovery was so important that we named the unit of electrical force after Volta himself, the volt. So what's actually going on inside the batteries you use every day? Crack one open and wait, don't actually do that. But if you could peek inside, you'd find 3 key ingredients. First, an anode. That's the negative side, usually made of something like zinc or graphite. Second, a cathode. That's the positive side, made of a different material like manganese dioxide. And third, sandwiched between them, an electrolyte, a chemical paste or liquid that connects the two but in a very sneaky, selective way. Here's where the chemistry gets wild. The anode's atoms are restless. Zinc atoms, for example, are practically begging to give away their electrons. It's a chemical reaction called oxidation. Each zinc atom releases 2 electrons and transforms into a zinc ion. Think of it like this. Imagine you're holding 2 glowing energy balls and your hands are on fire. You desperately need to throw them to someone. That's what zinc atoms feel like. They shed their electrons and immediately feel better. But those loose electrons now need somewhere to go. And this is where it gets clever. The electrolyte sitting between the anode and cathode has one very important rule. It lets ions pass through, but it completely blocks electrons. Picture a nightclub bouncer who checks for a specific wristband. Ions, come on in. Electrons? Nope. Turn around. This is the genius of a battery. Because those electrons from the anode can't cut through the electrolyte, they have to take the long way around. Through the wire, through your phone, through whatever device you've plugged in. That detour through the external circuit is your electricity. Meanwhile, on the other side of the battery, the cathode is waiting with open arms. It's made of a material that really wants electrons. When they arrive after their trip through the wire, another chemical reaction happens. This one is called reduction. The cathode's material absorbs the incoming electrons and combines with ions that traveled through the electrolyte from the other side. So you've got this beautiful loop. Electrons leave the anode, travel through your device, doing useful work along the way, and land at the cathode. A complete circuit powered by chemistry. But nothing lasts forever. As the battery runs, the zinc anode slowly dissolves. Atom by atom, it breaks apart and transforms into ions. Meanwhile, the cathode material changes too, filling up with the reaction products. Eventually, there's not enough fresh reactant left to keep the chemical reaction going. The battery dies. It's not that the electricity ran out. Remember, there was never stored electricity to begin with. The chemicals that make the reaction possible simply got used up. The factory shut down because it ran out of raw materials. Now, here's the really clever part. Some batteries can run the whole reaction backwards. When you plug in your phone charger, you're pushing electricity back into the battery. That incoming energy forces the ions back to their original positions. The dissolved zinc rebuilds itself atom by atom. The cathode releases what it absorbed. Everything resets, ready to react again. Lithium-ion batteries in your phone can do this hundreds of times. That's not magic. It's the same basic chemistry Volta discovered, just running in reverse. Charge, discharge, repeat. 200 years after Volta's stack of zinc and copper, batteries power almost everything around you. There are roughly 15 billion batteries sold every single year. They run your phone, start your car, keep hospitals alive during blackouts, and send rovers across Mars. The chemistry has evolved. Lithium replaced zinc. Solid electrolytes are replacing liquid ones. But strip away the fancy materials and the same principle remains. Two substances that want to react, separated by a barrier that forces electrons through a wire. Volta's dead frog would be proud. So the next time someone asks how a battery works, you can tell them the truth. A battery isn't a storage tank for electricity. It's a chemical engine. Two materials on opposite sides, desperate to react with each other, kept apart by a barrier that refuses to let electrons pass. The only path for those electrons is through your device, and every time they make that journey, they power your world. All because 200 years ago, a dead frog twitched, and a curious scientist asked why. If you like this video, check out one of these, and don't forget to subscribe.